Today, my presentation is about validation of new phase-dependent stability measures for walking. Falling is a major threat to the health of elderly people. Identification of individuals at high risk of falling is increasingly important. Current stability measures like maximum Lyapunov exponent or maximum frequent multipliers are limited in predicting force. This may be because they reduce stability to an average over the gait circle or a single point over the gait circle. Recently, phase-dependent stability measures have been used to has been used to quantify the intra-stride local stability changes in human gait, but it is unknown how this type of information can be used to predict force or how well it predicts. In order to validate the phase-dependent stability measures for walking, we test them on simple passive dynamic walkers to see the relations between these measures and gait robustness as an indicator of falling probability. The states of the walker are written in Hamiltonian canonical form, and the dynamics of a walker as a single stance phase and the instantaneous double stance phase. The right figure shows animations, the time domain, and the phase space representation in real time. Since the interlag generalized momentum is always close to zero, we only plot the remaining three states in phase space, which where we can find the periodic orbit in 3D space. To analyze local stability, we do some coordinate transformation such that the coordinate frame is always tangent and orthogonal to the trajectory. This is because if we perturb the system along the periodic gait, the system will remain on it and will only result in a phase shift. So for the purpose of analyzing stability, we only look at the moving Poincare section, which is always orthogonal to the tangent periodic orbit. After obtaining the local Jacobian matrix on the orthogonal hyperplane, we take the sum of all eigenvalues of this Jacobian matrix, which quantifies the expansion or contraction rate of the volume of all perturbed trajectories around the periodic orbit. This local stability metric is called the trajectory normal divergence rate, which is the blue curve on the right figure. And our phase-dependent stability measures take the maximum and the integral value, because the maximum tells us the local stability of the most unstable moment, and the integral value tells us the averaged redefined local stability of the swing phase. We compare the relations between phase-dependent stability measures and the gait robustness using two types of campus walkers, the point feet walker and the circular feet walker. For the point feet walker, we vary the configurations of it. We vary two configuration parameters of it, which is the floor slope and the mass ratio between the foot and the hip, which is every single point on these plots. For each configuration, we computed the phase-dependent stability measures as well as the maximum Lyapunov exponent, which is on the y-axis. For each configuration, we also simulated the model to work on the step up or step down perturbation at first step. Gait robustness is then quantified by the sum of the maximum allowable floor height variation of step up or step down. We can see that compared to the commonly used maximum Lyapunov exponent, the phase-dependent stability measures are more strongly correlated with gait robustness, which means that using phase-dependent stability measures are more accurate to predict gait robustness. So the question is, does this correlation also hold for on the different phase space representation or on the using a different model? We also write the dynamics of the system using Euler-Lagrange form rather than the Hamiltonian canonical form, and found that the first and three plots almost similar. But the second plot, which is a maximum trajectory, normal divergence rate correlation becomes worse, which I didn't put it on the slides. This means that stability metrics are dependent on the phase-space representation we use for the equations of motion. For the circular feet worker, we also vary the two configuration parameters, which is the floor slope and the foot radius. We can see that all three stability metrics becomes less well correlated with gait robustness. Even though the integral of the trajectory normal divergence rate is still positively well correlated with gait robustness, this correlation is completely different from the previous model where there's only negative correlation. To conclude, phase-dependent stability metrics may provide additional values in predicting force from people's daily life gait data compared to the maximum Lyapunov exponent. Phase-dependent stability metrics are strongly correlated with gait robustness, but this correlation depends strongly on our phase-space representation and the model, and varies a lot with different models. Our future work will focus on further developing phase-dependent stability metrics for different models and try to find the best phase-space representation for all models. Assuming we can find such a best stability metric, we are also going to develop implementation algorithms from people's normal working time series data. Thank you for listening.
Ask somebody else if they
Okay. Anybody else other than Andy?
Hi, Jian. Can you explain to me again what the difference is between this method and, let's say, normal maximum Lyapunov approach?
Okay.
Or Poincaré Floquet multiplier or something like that.
Okay. Maximum Lyapunov exponent and the maximum Floquet multiplier, they calculate stability measures from you look at the single point or the average local stability along the gait circle. And now phase-dependent local stability metric look at the intrastride local stability information and try to derive the useful information as the metric.
Yeah, Linda?
Yeah, I know the orbit's periodic, right?
Yeah.
Did you mean short time Lyapunov exponent or the actual Lyapunov exponent?
If it is small, yeah, the local
Because
stability.
I don't see how you could calculate that from a periodic orbit. Because you know it's an asymptotic thing for a steady state that's used on chaotic things. So
Yeah.
I don't. How are you getting Lyapunov exponent calculation
How do I
for
calculate
a
the
periodic orbit?
He's not. He's looking at the eigenvalues of the local Jacobian.
Well, but that's not the Lyapunov exponent.
No, but that's also not what he's doing, I believe.
Okay, then it's not the Lyapunov exponent.
Andy, you?
Well, is your number at some point in the cycle dependent on your coordinate choice?
Yeah, the values of the phase-dependent stability matrix depend on the coordinate frame we use, like Hamiltonian canonical form or Euler-Lagrange form. In the case of Euler-Lagrange form, the two angles would be the states we use might be the angle between the spring leg and the normal plane.
No, but if you did a change of coordinates,
Yeah.
and you look at the periodic cycle, the eigenvalues of the periodic cycle do not change when you do a change of coordinates. If you look at a fixed point, dynamical system with a fixed point, if you look at the eigenvalues, they don't change with a change of coordinates. But I believe that this thing you're looking at is actually dependent on the coordinate system you use.
Yes.
That's correct, is that right? So how do you ascribe any meaning to it? If you change theta to theta squared or log of theta or something, and the stability changes from unstable to stable, or what? How does it have meaning?
If we have the best phase-space representation, we want to use them to calculate the phase-dependent stability matrix, because Hamiltonian canonical form has some desirable properties, like the volume is preserved over the whole swing phase circle. So,
But there's more. But if it depends on which choice of Hamiltonian canonical coordinates, does it, or is it independent of the choice?
there's only one Hamiltonian canonical form,
That's
but there could be other forms. And we want to use the best phase-space representation because they are.
This sounds like a pencil and paper conversation to me.
I did. All right, let's thank the speaker.